Today we're going to look at lesson 10.2, which is talking about the areas of trapezoids, rhombuses, and kites. So remember from our lesson in 6.5 when we learned about trapezoids that the bases are the two sides that are parallel, the legs are the two sides that are not parallel, and then we have the height is drawn between the two bases at a right angle. So as we remember those things, when we look at the theorem 10.4, the area of a trapezoid is just 1/2 the height times the sum of the bases. So we're going to add the two parallel side lengths up, and we need to make sure we know the height, and we'll use those just to fill into the formula. So looking at example 1, they have a picture of Arkansas on the map, and they've drawn a trapezoid around it, and they're asking us to find the area of the trapezoid shown there. So the two parallel sides would be the top and bottom, and then the height would be the distance between those two. So I'm just going to write down the formula. And then I'm going to plug in the values. So I'll have 1/2 times the height is 242 miles. And then base 1 plus base 2 will be 250 plus 190. So I'm going to add in the parentheses first, and then I'll be multiplying everything across. So I'm going to end up with, I can go ahead and do half of 242 if I want. That's 121. And then 250 plus 190 is 440. Okay, when I multiply those together, I get 53,240 square miles. Now I can write with the miles with the exponent of 2, or I could write SQ period mile MI period. That's another way of abbreviating. Okay, so pause and try to use this formula on Quick Check 1 where they give you the height and the bases. Hopefully you worked this out, and now you can see if you did it correctly. So I'm going to have the area equals 1/2 times the height, which they told me here was 7 centimeters, and then times the sum of the bases, which were 12 and 15. So it'll be 1/2 times 7 times 12 plus 15 is 27. Now if you want to put this on your calculator and you don't like having to use a fraction, you can multiply 7 times 27 and then just divide by 2. When you work that out, you should get 94.5 centimeters squared. Okay, moving on to the next example. We have a trapezoid that I've drawn here, and I'm trying to find the area of it. They gave me some information about this trapezoid. We know that one of the legs is at a right angle to the bases, and the other is at a 60-degree angle here. So my height, I would have to drop down. If I knew the height from R to Q, that would be okay, but I don't this time. So, oops. I just moved my, just undo that. Okay. Let's see if we can draw the height in. My drawing's not very good right now for some reason. Alright, so I'm dropping down from S down to the base, and I make a right angle there. Since this is a right triangle, this top angle has to be 30 degrees. Okay, so I have the top base is 5. When I draw the height down to the bottom base, it's going to cut it in 2 pieces. One will be 5, so that's like a rectangle there. That means that this part of the right triangle must be just 2 meters, the part that's left to get 7. And I need to figure out what the height is. So what I can do is use the special triangles, the 30, 60, 90 triangle, we know the short side, and I know that the long side, the long leg of the 30, 60, 90 triangle is the short side times square root of 3. If you don't remember that, you could also use trig functions to find what that height would be, because you know the angle is 60, so you could do tangent of 60 degrees equals h over 2. But since we know the special relationships in the 30, 60, 90 triangle, I'm going to use that. So the short side is 2 times, I keep on doing that. The short side will be 2 times the square root of 3. I mean the longer leg, which is across from the 60, will be the short side times square root of 3. So once I figure out that that's the height, I can just use my area formula. So it'll be 1/2 times the height, which is 2 square root of 3, times the sum of the bases, which would be 7 plus 5. So when I multiply 1/2 times 2 square root of 3, I just get square root of 3, times 7 plus 5 is 12. So this will give me 12 square root of 3. Now if you did it on a calculator, you would get the decimal version of this, but this is in meters squared. Okay, now quick check 2 asks you to take this figure that we have above and just change it a little bit. Everything stays the same except for the angle of at P. Well, I should say not everything stays the same. The angles at R and Q stay the same. The lengths of the bases stay the same, but the height is changing so that we can draw a new figure. We want the measure of angle P to be 45 degrees. So if I draw that in, this is going to be hard to draw. That'd be usually if I draw it like this. Okay, so there's my leg. This time the height had to change, but we left everything else the same. So this is still 7 on the bottom for the bottom base. The top base is 5. My picture's not to scale, but this is a 45-degree angle. So when I drop my height down again, I'm going to get that this smaller part of the base that's left is 2, even though it doesn't look to scale right now. In a 45-45-90 triangle, the legs are the same length, so that tells me that the height will be 2 here. So now when I use my area formula, I'm going to have 1/2 times the height 2 times the sum of the bases, which is not going to change because we didn't change those lengths. So that's going to give me 1/2 of 2 is 1 times 7 plus 5 is 12. That's just going to give me an area of 12 meters squared. Okay, to the next example. All right, now we need to know how to find areas of a rhombus or a kite. So this theorem 10.5 is the same for both. I have a rhombus drawn in. It works for a kite too. If you look at it sideways, it kind of looks like a kite. But what happens is we have to just know the lengths of the diagonals, and then we can multiply 1/2 times the product of the diagonals. So let's look at example 3. Example 3 has a kite pictured, and they give me the lengths of the pieces of the diagonals, so I can figure out that the diagonal that's green is, we'll call it diagonal 2, just because I called it that in the picture above, is 3 meters plus 3 meters, which is 6 meters. Diagonal 1 is 2 meters plus 5 meters, which is 7 meters. So if I know those diagonals, my area will just be 1/2 times 7, which is the diagonal 1, times 6, which is diagonal 2. So that's going to be 1/2 of 42, which is 21 meters squared. So the main thing that's going to happen on these is that you're going to have to be figuring out what the lengths of the diagonals are, and sometimes it's harder to do that than others. All right, stop and try quick check 3, and then come back and see if you got it correctly. All right, so for this one, the area is 1/2 times the diagonals that they give me, 12 times 9. So I'm going to be multiplying 12 times 9 and dividing by 2. I should get 54 inches squared. All right, and finally, example 4 shows us a rhombus. So we're still using that same theorem, but this time the information that we're given leaves some things out. Now, I know that in a rhombus, the diagonals bisect each other. I know that the diagonals in a rhombus are also perpendicular. So here, I can draw in a right angle. And that will help me figure out what I need to know for the green diagonal that I don't have anything listed. So on AC, the red diagonal, since we know the diagonals of a parallelogram bisect each other and a rhombus is a parallelogram, I know that this other piece is also 12. Okay, but the green one I have no information on. So since I know that the diagonals of a rhombus are perpendicular, and I drew that in to be a right triangle, I can think about the Pythagorean theorem, and I know that, I'm going to call this A for now. I know that A squared plus the other leg squared, 12 squared, equals 15 squared, which is the hypotenuse of that triangle. So we're just looking at triangle BEC. Okay. So the hypotenuse was 15, one of the legs was 12, and the other leg we don't know. So I would be working this out. So A squared would be equal to 15 squared minus 12 squared. I'm going to work this out on my calculator in just a minute. So I would get A squared equals 15 squared, which is 225, minus 12 squared, which is 144. So I'm going to get A squared equals 81 when I subtract those. And then the square root of both sides would give me A equals 9. So now we know that this piece is 9, and the other piece has to be the same length. So my diagonal 2 will be 9 plus 9, which is 18. My diagonal 1 will be 12 plus 12, which is 24. So when I find the area, it will just be 1/2 times 18 times 24. And I'm just using my calculator to do that. I end up getting 216. Make sure you pay attention to the units. So we were in meters in this one, so this will be 216 meters squared. Okay, try the problems, and we'll see you in class.